Welcome back to Physics 142 online. I'd like to continue our discussion of harmonic motion by now spending some time taking into account the realistic situation where the object that's moving, even though it still undergoes a type of harmonic motion, encounters some resistance. And so a very, very simple way of achieving this is to have an object that moves through a fluid of some kind that's going to give a resistive force that depends on the velocity of motion. And so a simple mathematical model for this is just a linear proportionality between the damping force and the velocity in the direction that the object's moving, and b, the constant of proportionality, is called the damping coefficient. The larger b is, the stronger the damping force. And notice that the minus sign means that the damping force is always opposite to the direction of the motion. So with Newton's second law, we can now write down a more sophisticated equation of motion that includes not only the restoring force from Hooke's law, but also this damping force. And so we can set the sum of those two forces again equal to mass times acceleration in that direction, which is mass times the second derivative of position, and then rearranging this gives the equation of motion, which is now a second order differential equation, but notice now it includes not only the first derivative, but also, not only the second derivative, but also the first derivative, because the velocity, v sub x, is dx dt. So this is the standard way of writing this down, and this is a differential equation that has many, many physical applications in science and engineering. So I'm not going to show exactly how to solve this, but I'll show you the solution, at least the case where the damping is relatively small, so that the object oscillates back and forth, but has an amplitude that gets smaller and smaller. And you might even be able to come up with a pretty decent guess for what the solution to this equation should be. Remember that if b is equal to 0 and there's no damping, we already know what the solution is, and that it's got the form of a cosine omega t plus a phase constant phi. So what would be different about the solution to this equation physically is that the amplitude, would get smaller with time. So the system would oscillate, but that amplitude would get smaller in every cycle. And so it kind of makes sense to think that the cosine term will still be present in the solution, but that the amplitude might have, for example, just as a guess, a decaying exponential function. And it turns out that if we write down a trial solution that is the product of an exponential function and a cosine function, that actually gives us the correct solution. And so the way that this is commonly written is there's still an amplitude a, which represents the maximum displacement, but now, and there's still a cosine omega t plus phi, but now there's this decaying exponential where b is the damping constant and m, of course, is the system mass. Now, when we plug this into the equation of motion and simplify things, we find that it's a valid solution where omega is now slightly different and a little bit smaller than it was in the case of the undamped system. And that makes sense, because if the mass, let's say, is attached to a spring and it's moving through a fluid, if b equals 0, we would get just the familiar omega is square root of k over m. And now having a damping term present means that the frequency will be a little bit less than it was otherwise. And so that means it'll take more time to oscillate back and forth. And here is a schematic way of writing down this kind of a solution where you can see that the cosine oscillation is present, but each time the maximum amplitude gets smaller and smaller in response to this damping term. This, by the way, is referred to as the underdamped solution of this equation. There's actually more than one solution, and the underdamped solution, you might be able to guess why it's called that, but we'll move on to the next possible solution and realize that where it comes from is what happens if b gets larger and larger and larger. Eventually, what we'll see is that this frequency will get smaller and smaller, and if b has just the right value, the frequency will go to 0, which means that the system won't oscillate at all. And that's called the critically damped solution, where b gets just large enough to make this omega prime term 0. Then what that means is the system will return to equilibrium without overshooting at all. There won't be an oscillation, so it'll just gradually return to equilibrium, and it's critically damped because it turns out that this solution is the fastest return to equilibrium that the system can have without going past it. So schematically here is what the behavior will look like if we plot position on the y-axis versus time. We start off with some maximum displacement and then let go, and the system will return to the equilibrium position at x equals 0. At least it will approach that equilibrium in the shortest amount of time possible. Now what happens if b gets even larger than the special value that it has to have here is that we will have still a solution that does not oscillate. It'll still be this kind of a solution that will return to equilibrium without overshooting, but it will just take longer to do it than it does in this critically damped case. And so that's called the overdamped solution. So if the damping coefficient if b squared is greater than that critical value of 4 mk, then the resistive force resists the motion even more. And so by comparison, we can see schematically how this behaves. The blue shows us the previously plotted critically damped solution. The red shows the overdamped solution if b is even larger. So these are the three possible cases for the solutions to this damped harmonic oscillator equation of motion. So here's a quick example. Imagine that you're given a problem, and there's some homework problems similar to this, that says in one cycle of motion we observe a damped harmonic oscillator to lose half of its initial amplitude. So if the initial amplitude was 10 centimeters, we let it go, and after one oscillation it only comes back to 5 centimeters. So with that information, find an expression for the damping coefficient b in terms of m and k. So this, obviously, if it's going to oscillate and come back, although at a lower amplitude, this is underdamped motion, so we can use the solution, the underdamped solution, and we can plug in the x value for t equals 0, and then the x value for t equals 1 period, which is the time it takes for one cycle of motion. So to keep it simple, let's just assume that we have a situation where the phase constant is 0, since the problem didn't tell us anything about that. So it's just a pure cosine function. And at t equals 0, the displacement, of course, if we plug in 0, t equals 0 in both those terms, the displacement just gives us a. And then if we wait 1 period, so t is equal to capital T 1 period, we get a e to the minus bt over 2m cosine omega prime t. And of course, in one cycle, the cosine term returns to its maximum value of 1 again, so that the x of t is just going to be a e to the minus bt over 2m. So what do we do with these two equations? Well, we know that the amplitude, the displacement, after one cycle of motion is half of what it was originally. And so this second term is equal to half of the first term, right? X after 1 period divided by x initial is just 1/2. And so if we divide those two, the a cancels out, and we see that 1/2 is equal to e to the minus b times the period over 2m. Now, if I knew the period and the mass of the system, I could use this equation directly to calculate a numerical value for b. But let's assume I don't. Let's assume I just want to find an expression for b in terms of k and m. So at this point, what I would do is solve for t, and t would be 2 pi over omega prime, right? I could plug that into here, and then I would need to take the natural log of both sides, and that would give me an equation that would have b in it along with m and k. And I could try at least to solve that equation for b, which would give me how b would depend on the spring constant and on the mass. So there are various kinds of problems like this, but be aware that, again, it's sort of an initial value problem where we know what the initial displacement is, except now we know what the displacement is after one cycle. So we use the solution and those pieces of information to solve the problem. All right, let's finish off this chapter with a brief discussion of what the kind of behavior that you have when an oscillator that's free to oscillate back and forth doesn't do so on its own, but rather is subject to some kind of input. And so this is the case of forced oscillations. And there's something very interesting that happens called resonance under the right circumstances. So when the mass spring system is subject to a periodic external driving force, maybe you've got a mass on a spring and something is shaking the system, and it's shaking the system at a particular frequency. This might happen if you had the shock absorbers on your car, and then your car is driving over a road surface where there are bumps or there are cracks in the road surface at very specific distances, so that every time your tires would hit those cracks or those bumps, the car would shake, and there would be a well-defined frequency depending on the speed of the car. So that's a mechanical example. So what happens, we find out, is that if you do lots of experiments and measure the maximum amplitude of the system at different values of the frequency of the external force that's causing things to vibrate, you find that there's a peak. And the peak in that amplitude, the maximum amplitude in this situation for forced oscillations, happens when the external frequency is very close to the natural frequency of the system. Omega 0, remember, is square root of k over m. The peak isn't exactly at omega 0, but it's very close to it. And the point is that if B is very, very small, if the damping term is very small, then this peak is very high and very narrow. If the damping term is larger, this peak gets lower and it's wider. And so there's not nearly as sharp of a peak when you have large damping for a system. So resonance is the phenomenon where you get a large amplitude response of the system to a driving force, an external force, whose frequency omega, that's what we're plotting on the x-axis, is very close to the natural frequency of the system. And that can be desirable in some cases, but also very undesirable in other cases. And we'll talk a little bit more about that during class time. So, as I said before, when you've got a system where there's not very much damping, that peak is high and very narrow. And there's a quantity called the quality of an oscillating system. A system that has very little damping has what's called a high quality system, where Q is defined as m omega naught over b, and it's equal to approximately 2 pi divided by the fractional loss of energy of the system in one cycle. So if the system has low energy loss because of the fact that it's got low damping, then you have a very high quality system and a very sharp peak. If on the other hand you've got a large damping term, then what you get is a very low quality system. And quality is often defined for electronic circuits that have a natural frequency and then can be subject to external frequencies. So the quality of the system tells us how strongly it responds when it's driven at its resonant frequency. So we'll do a little bit more about this in class. This wraps up our discussion of the first chapter, the first section in the course, and I will see you in class.